So I want to talk about some recent work that we've been doing. So this is kind of an unpretentious papers. I'll mostly focus about the second one, although the original motivation came from this one, and there's also this follow-up, which is a tutorial that is currently in preparation. And so there was collaboration with Pedro and Carlos from IFUSP, Patrick from the University of Basel in Switzerland, and Michael and Mark from Trinity College Dublin. So, okay, so here's kind of what I want to talk about. I'm going to imagine a system, a quantum system that is continuously measured. And the kind of system that I'll have in mind is going to be a system in an optical cavity. So these are mirrors. And inside this cavity, you can have any kind of material or crystal or whatever you want. And you can pump light into this cavity. You can pump light into this cavity because this mirror is semi-transparent. So there's a finite probability that photons can get in or out of this mirror. And so not only can you pump it, but there are also photons leaking out. And this is how we measure this kind of system. We put a detector here, and we just collect the photons that are leaking out of the cavity. I'll discuss by the end of the talk a very similar construction with quantum dots in condensed matter. So the idea is going to be quite similar. But I think that the interesting thing about the setup is that what you get is a photon current. So you get a bunch of clicks in your detector. And these clicks, they form a time series, just a sequence of detections. And this is a completely classical detection, right? It's just a complete classical time series, but which is somehow reflecting the quantum system underneath. And that's the basic question that we ask is, what can we learn from the quantum system from this time series of outcomes? Now, I'll show you two scenarios, which we usually call jumps and diffusion. So quantum jumps, it happens when you have discrete clicks in your detector. So, every once in a while, there's one photon leaking out, and then you get a click. So you get, something here, and then silence, and then another click, and so on. I'll also discuss a way that we can turn this into a continuous signal, just like a noisy process, such as this one, and we call this quantum diffusion. Okay, so why study these currents? I mean, most of what I want to talk about today will focus on the properties of these currents. Of course, the first motivation is because this is actually what we measure, right? An experimentalist would be measuring these currents. And then you want to ask, what kind of information can you learn about your quantum system from these currents? But what I really want to focus on are the correlations within these currents. So, you can have some kind of average current. I'm going to call it J sometimes. But even though you have this super noisy process, there are correlations between the current at different times, right? And there's a lot that can be learned from the underlying system by looking at these correlations. One particular application of this that I'm currently quite interested in is metrology and using this to make very precise sensors. So one famous example are the gravitational wave detectors in LIGO. They use exactly this setup. I mean, in LIGO, they do have an optical cavity. It's kilometers long, the optical cavity that they have, but it's still an optical cavity. And they measure the gravitational waves using exactly this kind of setup. Another application that I'm interested in is what's called thermokinetic uncertainty relations. So these are relations that appeared in classical thermodynamics very recently, maybe 5 years ago. These uncertainty relations, they essentially provide a bound for the fluctuations of a given current. So J squared is the average current, and D is the variance of the current, the fluctuations of the current. And these uncertainty relations, they say that this must be larger than something which depends on the entropy production, which is a quantity in thermodynamics that is used as a measure of dissipation. Now, this result is actually counterintuitive because it says that if you want to reduce fluctuations, you actually have to increase dissipation. So, in undergrads, we learned that reversible processes are good and irreversibility is bad. But if fluctuation is an issue, then actually you might want to have a process to be more irreversible that can be used to reduce the fluctuations. But these are classical results. So these are derived from classical processes, and they can be violated in quantum systems. And one open question is, so if they can be violated, why? What's the reason why they're violated? And two, is there any other kind of fundamental restriction on the current fluctuations? Okay, so I'll focus most of my talk on this parametric Kerr model, which is a very cute toy model to play with these kind of phenomena. The model is as follows. So the Hamiltonian is just a harmonic oscillator. Here's the usual term, A dagger A. Then we have a Hubbard-like term, but like a Bose-Hubbard term, which is called, in the optics community, is what's called the Kerr nonlinearity. Is exactly the same, is not exactly, but it's pretty much the same one that Toninho Figueiredo was discussing this morning. And then we also have this, it's called two-photon pump, which is essentially a process that creates pairs of photons or destroys pairs of photons. And we also have dissipation. So we also have the fact that these photons can leak out of the cavity. And since they can leak out, there is damping. And we describe this using this called quantum master equation. And this kappa here is the damping rate. Now, this model is super simple. But it's the model that just keeps on giving, because it's been known since the 70s. And there's like so many cool stuff that you can actually do with this. In particular, this model actually has a phase transition if you play with the parameters. In particular, I show this here. So what I'm plotting is the photon number. So it's just the average A dagger A inside your cavity as a function of these two parameters, delta and G, with a fixed U and a fixed kappa. And what you see is that there are two phases. There is this inactive phase where pretty much the cavity is nearly empty. There's no photons in there. And then an active phase where the number of photons becomes very large. But this region here actually has two boundaries. So if you cross it from below, this is actually going to be a continuous transition. You can kind of see it in the color gradient here. But if you cross it from here, it's actually a discontinuous transition. Now, if you're a purist, you might say that this is not a proper phase transition. Of course, this is just a harmonic oscillator. There can be no critical phenomena. So what happens is this system becomes critical if you take this U to 0. So 1 over U is like your thermodynamic limit. It's not a proper thermodynamic limit. It just mimics the phase transition of the process. OK, and we can gain a bit more understanding about what's happening in this system if we plot the Wigner function. So the Wigner function is a quasi-probability in position and momentum. So you have a harmonic oscillator. Here's x, here's p. And so the plots start from the bottom and go up. So you see that in the bottom, your Wigner function is just a blob in the middle. We call this a squeeze state because it's not symmetric, so it's a little bit squeezed. But as you reach this first continuous transition, this blob becomes more and more squeezed until eventually it splits into two blobs. Then as you keep moving, the two blobs eventually become 3. And then at this point, the discontinuous transition, the 3-blob structure becomes unstable. And it collapses again into just one squeezed blob in the middle. OK, so this model, as I mentioned, is the model that just keeps on giving because it's been known for a long time. It's fairly simple, but there are so many interesting applications that keep coming up. In particular, in maybe 3 years ago, 4 years ago, they started to be used as candidates for encoding qubits in quantum computers. The logic is that if you have a state like this, you can pretty much encode this as a logical qubit, so a 0 and a 1. And so if you have a system with multiple optical cavities, you can actually use this as a quantum computer. And this is nice because the quantum computers that are being used nowadays, which use superconducting qubits, they actually can already implement this Kerr model. If you look at the superconducting junction that they use in there and interact it with an optical cavity, it will actually implement the Kerr model. So they can actually do this on kind of similar architectures that the ones that are already being used. And one of the advantages of this is that, in particular in this paper, they show that this is quite resilient to noise. So the big problem of quantum computers today is that it's noise. Noise ruins everything. And you can use this kind of encoding of a qubit to protect from noise quite efficiently. Sorry, I just forgot to mention. So people call these cat states. just because, not exactly this is a cat state, but this would actually be a cat state. It's just a macroscopic superposition of two very different results, because these blobs, they're very far apart. So it's like, have one kind of macroscopic state here, one here, but you're in a superposition of the two of them. So it's like Schrodinger's cat. OK, you can do a mean field approximation and come up with a classical model, essentially replacing the annihilation operator A by just a variable alpha. You get some kind of equation like this. You can look at a kind of bifurcation diagrams of this kind of equation. So this will predict the continuous transition. So this black line here is actually exactly, this curve. So it will predict that there is a continuous transition as you move up here. There is no semi-classical model that can predict this red line here. So this red line is actually a guide to the eye. It's not a theoretical prediction. And the reason, I mean, as far as we know, the origin of this red line is really the quantum fluctuations that appear in the model that make the three blobs unstable. Yeah. Oh, sorry, this is from an old talk. Sorry. This makes no sense at all within this context. Yeah, OK. So now I want to imagine what happens to this model if we look at the current. So we go to the lab. This is all theoretical, of course. But we go to the lab and we measure the photons that are leaking out. We can actually simulate this using this quantum jump unraveling. It's a technique to stochastically simulate these quantum jumps in the system. The idea is fairly simple. You integrate your equations. And at each time step, you decide if a jump is going to occur or not. The probability that a jump occurs is proportional to the average number of photons. So if there's a lot of photons, there's a big probability that the photons are going to leak out. I mean, makes sense. But it's also proportional to dt. So most of the time, actually, no jump occurs. If a jump occurs, essentially, you just apply A operator to psi. If no jump occurs, then the system will evolve with a non-Hermitian Hamiltonian. I maybe don't need to go into the details of why it's a non-Hermitian Hamiltonian and not a Hermitian Hamiltonian, but that's what it turns out to be. And so if you were to look at the average photon number, you might get something like this. You get these continuous evolutions where the system is just wiggling around, and they're interrupted by these abrupt quantum jumps. OK, so now what I'm actually going to show is what happens to these quantum trajectories if we look at this instability point. So more precisely, immediately below this transition here in the blue point. So what we get is actually this, is a series of jumps occurring in close succession to each other, followed by dark periods. And so essentially, the system is either emitting a lot of photons, or it's just dark. There's no emissions. And this is related to the photon number inside the cavity. So this is how many photons there are in there. And you see that in the bright phase, there's a lot of photons. And then in the dark phase, there's pretty much no photons. And so if you take this and you integrate this over time, you can get what we call the dynamical activity, which is just the jumps per second. So the average current would just give you how many jumps per second is happening here. But this is not as illuminating, because the average doesn't tell you about this very interesting structure, that you have dark and bright periods happening in succession. And this is closely related to the Wigner function, as I will discuss. So to see that, to see that, we need to look at 2-point correlation functions. So we can look. So sorry, I actually forgot to mention. Every time there is a click, we define a variable dn, which is incremented by 1. And then the current, the photon current, is just dn dt, right? So essentially, what is being plotted here is actually not really the current, is dn, right? It's just 0 or 1. OK, so now we can actually look at the 2-point correlation function. So this is what's written in the first line is the classical 2-point correlation function between this classical stochastic current. And this can be rewritten into 2 terms. There is a kind of equal time correlation, which is actually infinite, plus a term which is widely studied in quantum optics. They call this the Glauber's second-order coherence function. And this can be computed numerically. And we can also Fourier transform and get the power spectrum. Just to be a bit simpler, I'm going to focus on S of 0. So this is the 0 frequency component of the power spectrum. And it's nice that one can also show that the zero frequency component is actually the DDT of the variance of the number of total number of clicks that you get. So this is a result from Foucaultian statistics. Yeah. OK, so this is what we get for the discontinuous transition. Sorry, for this diffusion coefficient, which is the zero frequency component of the power spectrum. We get that it actually diverges exponentially in the discontinuous transition. So here, what I'm plotting is this d as a function of delta for a fixed g. So I'm essentially going this way. And you see that it will diverge around this black point as well. But this is going to be an algebraic divergence. But then in this discontinuous transition, it will show an exponential divergence of the with respect to 1 over u. So as I mentioned, 1 over u plays a similar role to the to the volume, to the number of particles in your system. And so this will show a kind of similar exponential divergence.
What are the colors there? What
Right. Yeah. So these are for different values of 1 over u. So essentially, yeah, this would be small u and large u. Yeah. So this can actually be understood. There's been a couple of papers, including one with me and Fiori, that I mentioned in the beginning, showing that the noise, this diffusion coefficient, it always diverges exponentially in a first-order phase transition. This is a consequence of the fact that, if I may just go back here for 1 second, is a consequence of the fact that the tunneling times between the different blobs, they diverge exponentially. OK, so in this paper in 2018, they actually implemented experimentally a very similar model. It's not exactly the same, but it's very similar. And so they also observed this kind of transition between active, inactive phase and a situation where it's pretty much there's nothing in there, so the inactive phase and the active phase. And they compute this diffusion coefficient, and they also find an exponential divergence. It's funny that they mentioned that from the data, it seems that it's exponential, but we cannot really be sure. And we have no kind of reason to, no physical arguments as to why it should be, but the data kind of points out that it's exponential, and our model can actually show that this is exponential from these simulations. OK, so what I talked before is quantum jumps. So it's essentially, most of the time you get silence. Every once in a while you get a click. We can also turn this into a diffusive process using something called a homodyne detection that is well known in optics. Homodyne detection is essentially you get the photons that are leaking out of your cavity, and you mix it with a very strong laser. So you mix the photon signals. And what happens is that instead of measuring the number of photons like A dagger A, what homodyne detection does, it measures A plus alpha dagger A plus alpha, where this alpha is something where the magnitude is the intensity of the laser, and the phase is related to the phase of the laser. You can, in principle, tune this phase phi here. And so if we expand this out, we get a constant term. I mean, this part is simple. We can just subtract it out. It's like a very strong signal. We can just take it out. And then we get, and this is the interesting part, you get a term that's proportional to alpha, which is actually measuring not A dagger A, but is measuring A plus A dagger with some phases, plus the term that we were measuring before, A dagger A. And so if this alpha is very strong, this term will actually be dominant. And so essentially, you'll just be detecting a different operator. And that's the cool thing about homodyne. Homodyne doesn't measure the photon number. It measures essentially the position and momentum of the harmonic oscillator, which they call the quadratures. Just as a quick parenthesis, the way we simulate this is called the quantum diffusion unraveling. Essentially, you get your quantum master equation, and you append to it something. You make it into a multiplicative noise Langevin equation by adding some Wiener increments. And this is the way that this is simulated. There's, of course, proper arguments as to why this is the correct model. Yeah, OK, so this is what we get. So what I'm plotting here is actually the quantum trajectories of the system in position and momentum overlapped with the Wigner function that we had before. So now this explains what, of course, intuitively we expected. The system is essentially jumping between the three blobs, right? It spends most of its time in the 3 blobs, and then eventually sometime, kind of transitioning in between them. Now, this is what you would actually measure in an experiment. You measure a current. This is a filtered current, so we have to run it through a filter to reduce the noise a little bit. But you get something which is essentially a 3-state model. So it's either around 0 or negative, maybe around 4 or something, or positive around +4. And so this is fundamentally different from the current that we had before. Photo detection can know if the system is in the middle blob or in the outer blobs, but it cannot know if the system is here or here, right? But homodyne can. Homodyne can distinguish if the system is in the top blob or in the bottom blob. And so, for example, the photon number, it's high when the system is in the bottom blob and high when the system is in the top blob, but you cannot really know which blob you are. But with homodyne detection, you can actually distinguish the two. OK, and this is what we get for the diffusion coefficient. We get that it actually diverges exponentially in the entire critical region. Now, we don't have a good physical argument as to why this must be so. But essentially, in the entire region, not only in the critical lines, in the entire region, it diverges exponentially in this way. OK, so now I mean, this is pretty much the message that I wanted to say. As I mentioned, this is kind of an unpretentious work. We just had a lot of fun playing with this model. It's a super interesting model. And we're just playing with understanding current fluctuations in this model. Now what we're doing is we're applying this to a couple of scenarios. One in particular is, as I mentioned before, is metrology. So metrology essentially means, we have the parameters in our model, and these parameters, they encode some physics that we want to measure, maybe some magnetic fields, for example. Or, for example, you can also use this as some kind of photon detector to detect single photons and so on. And what we want to do is see if we can use this as a very precise way of measuring this parameter. So for example, if we stop around this region, if we suppose we encode in this parameter delta something that we want to measure. Now, if this thing is immediately above, then we get no signal. As soon as it's below, we start getting a bunch of clicks. So this is a very precise sensor because you have a very sharp transition. As soon as this delta changes, you'll start observing a lot of clicks, and then you know that your delta has changed. So you can use this for sensing. Another thing that we're trying to do is use this for thermometry. Can you actually make a thermometer out of this? And this is also related to a quantum dot setup. So pretty much everything that I said can be translated, especially like the equations and the Bain ideas. They can also be translated to a quantum dot setup if you use what's called a quantum point contact. So a quantum point contact is essentially, so here's your quantum dot, which can have either no electrons or 1 electron. And it might be connected to reservoirs. So eventually, an electron is going to jump from here to here, or from here to here, and so on, right? A quantum point contact is just a wire, which has a constriction. And so the current is constricted here. And this current flow is going to be sensitive to the Coulomb interaction of this electron. So if there is an electron here, the current here would change. And so by putting a quantum point contact next to the quantum dot, you can actually continuously monitor the occupation of the dot. So it would be just like we were measuring the occupation of the cavity. Here you can measure the occupation of the quantum dot. This is from the people in Basel, an experimental paper, where they compute the output current that you get in this quantum point contact. And you observe the same kind of telegraphic behavior that we found in the Kerr model, where essentially the system, it's either active, and it's active because there is an electron there, or it just jumps down because there's no electron there. And one of the things that we're trying to do, for example, is can we use this as a thermometer? By monitoring the time between jumps, how much time does it take between a dark and a bright phase? Can we actually use that to just measure temperature, for instance? OK, so this is kind of the summary of the talk. Essentially, this is one of the problems that I'm quite interested in at the moment, this correlations in a classical time series and relating them to continuously measured quantum systems. And in particular here, I focused on the Kerr model and on 2 detection schemes, the photo detection and homodyne detection. For photo detection, you get an exponential divergence at the discontinuous transition line, and this is explained by other results in first-order phase transitions. For the homodyne detection, you get an exponential divergence in the entire critical region, and this is still an open question. OK, and I just wanted to mention, so recently I started working as an editor for PRX Quantum, and I wanted to take 1 second to advertise the journal. So PRX Quantum is a new journal from APS. It's meant to be PRX level, so high impact, high quality research, fully open access. And it welcomes any contribution in quantum information sciences and technologies, not only hardcore like quantum computing, that kind of stuff, but much broader theory, experiment, also going beyond to engineering, mathematics, computer science, and so on. So it's a very broad journal trying to encompass all about quantum technologies. So that's, I guess, what I had to say. Thanks very much.
Thank you, Gabriel. We have time for questions.
Hi, thank you for your talk. It's more about curiosity because I know it's not the main focus, but do you know the mechanism for the cat state to be robust against decoherence?
Right, so let me see if I can, sorry, if I can go back. Oops, I guess I can't. So pretty much it's not robust against any kind of noise. So most of the noise, so there are two sources of noise in quantum computers called bit flip and phase flip. This is not robust against phase flip, but it's very robust against bit flip, just because these are like just two almost macroscopically different states. So to have a bit flip, there's a big cost in here. But it is more sensitive to phase flip, actually. It's worse for phase noise. Phase flip, sorry. But phase flip is something that you can correct very easily with quantum error correction. So bit flip is much harder to correct. And so the advantage is you protect against bit flip, and then you use error correction algorithms to resolve for the phase flips.
So, Gabriel, very nice. So at the end, you commented on a quantum dot inside a cavity or a constriction. So how important is what you put inside your cavity for your model? So,
right.
Because I don't know if you heard about quantum dots. There are some quantum dots that blink. It's very similar to this.
Right.
So how important is it?
Right, so that's a very good question. So yeah, quantum dot blinking is one interesting application of this. I have some friends that are working on trying to understand like the mechanisms behind blinking and so on. So as far as the physics is concerned, what you put inside the cavity matters a lot. I mean, that's pretty much what determines the model. So if you don't have, let me just try to go back 1 sec if I can. One more, yeah. So, this is pretty much what you put inside the cavity. And this is well, to be fair, these are both actually a consequence of what you put inside your cavity. If for example, your cavity is empty, you wouldn't have these two terms. And so they know, for instance, that the type of crystals that you put in, like if you put a crystal, for example, it might lead to the chi2 and chi3 nonlinearities, like Toninho was explaining this morning. But you can also put like a single qubit inside the cavity, for example, and that would also lead to some kind of nonlinearities. So essentially, I mean, the physics will be strongly, strongly influenced by what you put inside the cavity. This kind of Kerr model, with some variations, maybe there can also be like a linear term, which is like A plus A dagger. I mean, they appear very often as effective descriptions of more complicated processes. So for example, if you put a superconducting circuit inside your cavity, the Hamiltonian is going to be much more complicated. But in some regimes, it can be approximated by this one. So this is like an effective description of that. Yeah.
So thanks, Gabriel, for this really nice talk. So I'm just wondering, I mean, what determines this maximum number of photons here, 8 in your model? And I mean, do you have any physical argument why do you get this exponential in 1/u?
Right, yeah. So the number of photons here is determined by the parameter u. So you see that I'm plotting photons per volume, right? So 1/u is volume. So I'm plotting A dagger 8 times u. And so essentially this, if you take u to 0, this diverges, right? So essentially this, it's not that you have 8 photons in your cavity. I think, for example, this simulation, this was u equal 1/10. So actually you have 80 photons inside the cavity and so on. And if you keep decreasing u, it just diverges. It diverges because if u is 0, the model becomes unstable. So if you actually started with u equals 0, it would be completely unstable. And sorry, what was the second question? Right, so the exponential is essentially, I mean, we do have a picture in terms of like, if you have a double well, the system can be either here or here, and there are some fluctuations which are like within well fluctuations, like it's fluctuating here. But there are also some fluctuations associated to interwell jumps. And these interwell fluctuations, they scale with the tunneling time, which itself scales as 1 over u. And so that's part of the reasons, just because the interwell fluctuations, they diverge.
Yeah. Just a curiosity, you mentioned that the evolution is with a non-Hermitian Hamiltonian. And that's natural because it's an open system, but apparently it doesn't decay, so because it keeps having the same sort of baseline current. So is this one of those non-Hermitian PT symmetric Hamiltonians that balance gain and loss?
No, so I mean, not really. It turns out that this could be a way of simulating PT symmetric Hamiltonians with balanced gain and loss. But the reason why you get a non-Hermitian Hamiltonian is, I mean, naively we would think that if no jump occurs, the system is just evolving unitarily. So it's like either a jump occurs or the system is just wiggling around. But the fact that no jump occurs also changes your information about the system. So for example, if you have a qubit that starts in the excited state and it's been 2 hours and no jump occurred, that will help you update your knowledge of where the system actually was initially. So that's why you get a non-Hermitian evolution. Overall, the system still evolves without losing any kind of probability or anything. So this has to be compensated. I didn't put the normalizations here. Like even this one, right? It's not normalized. So this has to be properly normalized. So the system doesn't lose probability, but it just evolves with this non-Hermitian Hamiltonian just to keep track of the fact that no jump is still something. It's still a measurement, right? If you measure something and you don't observe anything, that's still information.
Okay, thank you.
Okay, let's thank Gabriel again.
Thanks.
The next talk will be given by Vivian.